Hello students, in the last video we have discussed about pumping lemma for regular languages and its closure properties. So in this video we'll discuss about Myhill-Nerode theorem, minimization of finite automata. Of course, even this Myhill-Nerode theorem also will use to minimize the finite automata, and other way is state equivalence method. So we'll discuss both. So first of all, what does it mean by minimization? See, as I told you, if you are saying that it is a regular language, then that can be accepted by a finite automata or a regular expression or a regular grammar. That doesn't mean that if you are having L like ends with A, assume that ends with A, so the minimal states would be 2. But that doesn't mean that we can represent only in this way. There is no such concept. Okay, there is no such concept ends with A. Right? For example, if this is the correct automata, we can go for the 3 states, right? Same thing. So B, A, right? You can write here A, then B. You can go for one more state, no problem with that. You can go for one more. Same language is represented with 2 states, and here 3 states. Somewhere we may have 4 states, but the language accepted by all these machines are same. All means whatever we are constructing for it. But how to find the minimal method? You have done with the 3 states. These 3 states may or may not be minimal. How to find it? For that we use the 2 techniques. One is Myhill-Nerode theorem and another one is state equivalence method. First of all, what does it mean by a minimal automata? It should not have the unreachable states and it should not have the equal states. What does it mean by unreachable? A state which is not reachable from the starting state is called unreachable. So by default, you have to eliminate such states. You don't need to look for anything. If you are given an automata and you are asked to check for the minimal automata, first just remove it. Remove all the unreachable states where it is final or non-final, the states which are not reachable from the starting state. Like for example, you are having A here and B, you'll be having B. Assume that we are having C, A and B, and this is A. Starting state, assume that. From A I can reach B. I cannot reach the C. C is unreachable. Even though it is a final state, but something we cannot reach from the starting state is unreachable. So you can delete it. And you can go for the equal states. How to find the equal state that we'll discuss with the Myhill-Nerode theorem. Right? Or okay, before going for that, we can go with the equal states. Let me explain this with a simple example. Assume that we are having an automata like this. A 0, B is the final state, 0, 1, 1, 0, 0, 1, sorry, 1, C and 0. Right. We are having 3 states. First check whether do you have any unreachable state or not. Of course, no unreachable state here. From A I can reach the B, from A I can reach the C. Does that mean reachable means no, there is no concept of direct edge. Something we cannot reach with the path, that is unreachable, but we can reach from A to C. No unreachable states, equal. Take the pair of each and every 2 states, like we'll be having AB pair and BC pair and AC pair. Take it. And see guys, the pair of final and non-final never be equal. A is non-final, B is final, so never be equal. B is final, C is non-final, never be equal. A is non-final, C is non-final. We can even check, at least we can check it for this, whether they are equal or not. We can check it. Do it, how we can do that. So now take A and C. So how can you say that 2 states are equal? Take any string. If you read on A, they must give either 2 final states or 2 non-final states. For example, you take epsilon. On A, if I read nothing, I'll go to A. C, nothing, I can go to C. So both are non-final, non-final, no problem. Read 0. A0 we are going to B, C0 we are going to B. Both are final, no problem. 1. A1 we are going to A, B1 we are going to, C1 we are going to C. Both are non-final. Like that, till how many we have to check? How many states we are having? 3. Then you can go for 2. AA, 0 AA, 0 0 on A, we are going to B, 0 0 on C, B. Both are final. 1 0. A 1 0 going to B, B. 1 1. A 1 1 A, C 1 1 C. Right? 0 1. A 0 1 C, C 0 1 C. Now I can conclude that A is equivalent to C. You may get it out. Why you are concluding it? As I told you now, we are having n equivalent to 3, then take the length of the strings less than 3. So I took 0, 1 and 2. That's enough to prove it. So A and C are equal, then you can minimize like this. A and C are equal and B is not equivalent to any other state. A is 0 we are going to B, A1 we are going to A, B0 0, B1 we are going to C. C is already there. This is the minimized finite automata. This is how we are going to do it with the equal states. Same thing will apply it on the state equivalence method. So before going there, what does it mean by Myhill-Nerode theorem? See, if you are having an automata like this, okay, with the 4 states, what you can do, guys? Myhill-Nerode theorem, take the table where the number of rows and equivalent to this, then we can say that this is Q0 and Q0. Every state is equivalent to itself, don't consider it. And this is Q0 and Q1, you check it. Q0 and Q2, you check it. Then Q1 and Q0. If I prove that Q0 and Q1 are equal, no need to prove Q1 and Q0 are equal. Or if I prove that Q1 and Q0 are equal, you no need to prove it. Same way, Q1, Q1, a state is always equivalent to itself. And next Q1, Q2. So Q2, Q0. If I prove that Q2, Q0 are equal, you no need to prove that Q0, Q2 are equal. Same way, Q2, Q1. If I prove that both are equal, you no need to prove it again. Then Q2, Q2. So no need to say that. See the Myhill-Nerode, right? So this we have to check it. Now by using the state equivalence method, whatever we have discussed just now, we can verify whether these two are equal or not. Q1 is final, Q0 is non-final, so not equal. Q2 is final, Q0 is non-final, not equal. Q2 final, Q1 final. Then you have to check whether these two are equal or not by doing like this. Q1, Q2 string, epsilon Q1, Q1, Q2, both are final. A, Q1A we are going to Q2 and Q2A we are going to Q1, no problem. Both are final. B, Q1B we are going to Q1, Q2B we are going to Q2, no problem. Like you check AA, AB, PA, BB, anyway you'll get the same like final and non-final. Whenever you get a combination of final and non-final or non-final and final, you can conclude and you can say that Q1 and Q2 are not equal. But you do it, either you'll get two final or non-final. Right? And you may get a doubt, sir, why didn't you take the Q3? Because Q3 is unreachable state. Don't waste your time by dealing with this Q3. That's the reason even I didn't take it. You may get a doubt that why you didn't take the Q3. That's what I told you now. First and foremost thing is remove the unreachable state. Otherwise, the time is going to be wasted for you, right? What is the need of it if it is unreachable? So that's how it is going to be. The next one is state equivalence method. Why we are going for it? For example, if you are having 10 states, who will construct this table, guys? The Myhill-Nerode theorem of 10 rows and 10 columns. It's a waste of time, right? So to overcome that, we are going to have the state equivalence method. So first and the foremost thing is we have to divide the states into two groups. One is final and non-final and call it as P0. So, and if any two states in the same group are having the different behavior, then split it, right? And there is no concept of merging, guys, only splitting. And you have to repeat this splitting process until the current partition is equivalent to previous partitions, or if every partition is having only one state. So for these two conditions are met, you have to repeat the step 3. Of course, you might be having some doubts in this, but let me explain with the example, don't worry. So you'll definitely understand it. Let me go with this. Here we are having 5. First, in P0, divide the states into final and non-final group. What are the non-final states? Q0, Q1, Q2, Q3, and Q4. These are final. And specify the behavior of each and every state like this. See Q0 A where we are going 0, Q0 0, Q1. Don't tell in terms of the state names, tell me in terms of the partition names. Non-final partition, final partition. So Q0 0 we are going to Q1, Q1 is in non-final partition. Q0 1 we are going to Q3, Q3 in non-final partition. The same way you write it. Q1 0 we are going to Q2 in non-final partition. Q1 1 we are going to final Q4. See Q0 and Q1 are having different behavior, you separate in the next step. Same way you write it. Q2 0, Q1 non-final partition, Q2 1 final. See these two are having same behavior. So in the next step Q0 is 1, Q1, Q2 another partition. Write down Q3. If Q3 is having behavior like Q0, Q0, Q3 one partition, Q1, Q2 another. If Q3 is having a Q1, Q2, combine it. If Q3 is having a different like fine line and divide it. Q3 0, Q2 means non-final, Q3 1, Q4 final, right? So in the P0, what you can do here, in the P0, P1, see these groups are having different, like Q0 is having a different behavior than other, and Q1, Q2, Q3 are having same behavior, and Q4. Where we have to stop it or continue, check it. Is P1 groups are equivalent to P0? No, then continue it. But give it different names for the state, guys. Like this is NF1, NF2, F. Now specify the behavior based on the NF1. Don't check it because it's having only one state, no need of splitting. Don't merge anyway. Don't check this. Why? That's why I didn't check it, because there is no possibility of merging. Then what is the need of it? There is no possibility of merging and no splitting here, right? Then check it. Q1 0, where we are going Q2. Q2 is NF2. Q1 1, where we are going F, and Q4 means F. Same way you write it. Q2 0, NF2 only. Q2 1, you check it. Check the states and write. Don't write it blindly. Same way you can go for Q3 0. We are going to Q2 is in NF2, Q3 1, F. Any changes in this behavior? No. Then write down the P3. Sorry, P2. Now Q0. Any possibility of division? All are same behavior. No possibility. Q1, Q2, Q3, and Q4. Now we have to stop. Why? Because P1 is equivalent to P3. You have to stop. How many groups? 3 groups or 3 partition. Then I can say that 3 states. What are those? Q0 is one state. Q1, Q2, Q3 is another state. And Q4 is another state, final state. So Q0 0 where we are going Q1, 1 we are going to Q3. Both are here only. Q1 0 where we are going Q2 here. Q2 1 we are going to Q4. Q4 0 and 1 we are going to same state. So this is the finite automata and this is the minimal finite automata. So that's how you are going to find the minimal finite automata. So guys, the next video will discuss about grammar notations and derivations.